Okay, so I'll be doing problem 2.6 from rotational motion 2. So just to get an intuitive feel of the problem, what we should first do is diagram it. So I basically just drew a torque diagram because basically what we're given is that uh, we're told that every 100 years a frictional force increases the Earth's rotation period by 0.0016 seconds. So, if the frictional force wasn't there, it would just be rotating at a constant velocity, which basically tells us that the frictional force is the only force that's actually exerting a torque on the Earth. So now jumping the A, now that we got an intuitive feel for it, the angular acceleration is going to be equal, just in general, to omega final minus omega initial over delta t. So, really quick, just to figure out what the rotation period is by itself so we can get our omegas in terms of radians per second, we know that 24 hours is just equal to 86,400 seconds, which is where you can see we get the 2 pi radians in 86,400. 0.0016. That's going to be the final because it increases every 100 years by that number. And over here, we're going to have the normal rotation period of 86,400 seconds. And in the denominator, which is the delta t, we're going to have 3.15 times 10 to the 9th seconds because that's what's equal to 100 years. So that's the period it takes to do that. So just plug that into your calculator and then you'll get the final answer of negative 4.275 times 10 to the negative 22 radians per second squared, which will be our angular deceleration of the Earth. Now we jump to part B, which is where we're required to find the torque that the tides exert on the Earth. So we can easily plug in our angular acceleration. So we want to use this formula, which is the net torque is equal to moment of inertia times angular acceleration. So just really quick to make sure that we're on the same page and it's intuitive, like I already showed up here, the only force that's going to be affecting torque is the frictional force, which means that the net torque is just going to be the frictional force times the radius from the center. So this will give us that the torque of friction is equal to 2/5 mr squared because it's a sphere, and we're assuming that it's completely uniform, times the angular acceleration. So, just looking up what the mass of the Earth is online, we get 5.97 times 10 to the 24th kilograms, 6.371 times 10 to the 6th. Sorry, those should actually have units. Those units will be, that's radius, that's going to be meters. And then we have that squared times the angular acceleration. Now, plugging those numbers in, you'll get negative 4.15 times 10 to the 16th Newton meters as our torque exerted by the tides. Lastly, in part C, we're given, we want to determine what the frictional force is. So we found what the torque was, and looking it up, because the question asks if the tides were concentrated on the equator, you just look up on the internet the distance of the center of the equator from the center of the Earth, and this is what you get. It's essentially the same thing as the radius, but small deviation. So just divide both sides by 6.378 times 10 to the 6 meters, and you get a frictional force of negative 6.6 times 10 to the 9th newtons. Obviously, this depends which you designate as your negative and your positive. I made it negative, so the frictional force would also be negative in the right direction, or whichever direction you choose to designate. Cool.